We're here. There aren't very many meetings in this class at all. This is the last lecture. Wait, here, yeah. So I'm going to cover the last two chapters today, and I'll try and demonstrate the next couple of projects. We'll see how that goes. Controlling a Windows machine from campus is extremely difficult. All right, because they block everything useful on the campus firewall. So anyway, let's do chapters 5 and 6, and then I will attempt to demonstrate some projects if I can punch through the City College firewall. So, we're going to talk about mitigation of DNS service disruption. I want to check my streaming. Okay, streaming is probably good enough. All right, so if you want to resist denial of service attacks, which remain a really big problem and brought down a bunch of Azure last week and Office 365 too, I think. Even Microsoft can't seem to keep their things up in the face of these attacks. So you need to figure out how to protect your DNS servers. The authoritative servers are used for people outside your company to resolve domains inside your company, so they have to remain available to everybody on the internet. And that means anybody can flood them with unnecessary traffic. Now, a network distributed system will place copies of that server in multiple networks. You can do it on a small scale with different subnets, and on a large scale with different autonomous systems, which means owned by different companies, like different internet service providers. You can also do geographical distribution, which is the strongest of all, where you have them in completely different countries, completely different locations, so that if one whole area goes down, another whole area can take up the traffic. So to protect you from denial of service attacks, you can host your authoritative DNS servers at a content distribution network. There's a few of these. Akamai is the biggest, most expensive, and most famous. Cloudflare is one of the others. I think Azure has some CDN features now, and I think Google does. And so you can purchase caching acceleration services, which will provide a DNS server, which is supposed to be faster and more reliable than yours, where you redirect DNS traffic to there. But the problem is the authoritative server is still needed to be the first query that leads you to the second one. So if your authoritative server is down, you still won't be able to reach the caching acceleration service. A direct delegation is better, and that's what Cloudflare uses. So here's caching acceleration. Where is this website? And it tells me, well, it's a CNAME for a different name, and that's down here at the cache. And then you go to this cache server, which can handle a lot of traffic. But if somebody floods this server and takes it down, you won't be able to find where the cache is. And you can protect your domain with Cloudflare. I don't know if I got this in the projects anymore. I think I don't, but Cloudflare is a good service. You make them your authoritative DNS server, and then all your traffic goes to Cloudflare first, never anywhere else. And you trust them to stay up because they are geographically distributed, very strong network, almost impossible for anybody to take down. All right, and they're protected by Anycast. So is the root of DNS and all the really high availability services on the internet. Anycast means you configure multiple devices with the same IP address in different geographical locations, and then Border Gateway Protocol will redirect traffic to the nearest one that is up. And this works extremely effectively because it means not only are customers automatically redirected wherever they have to go to find one that's up, it means if you try to attack them with a DDoS attack, the attack traffic is distributed around the world. So you have to take down all the servers everywhere to bring it down. And that has turned out to be extremely effective. So here's what you have. You have Cloudflare. If you do a dig on my website, it will send you to Cloudflare servers. And so everybody trying to get to any of my pages first goes to Cloudflare for DNS resolution, and they are very strong and always up. I think they've gone down something like twice in the last 10 years briefly. So they're very good. All right. So there are some authoritative servers that are not available to the whole world. And this would be if you have a second authoritative server just for your own users. And I think City College is this way now. If you're on campus and you resolve the authoritative server, you get a strange IP address different than you get off campus. So it looks like we're doing this now. We have separate servers for on campus versus off campus queries. And all right, so Alta DNS does this. So when you can place an authoritative server inside the company for internal traffic, and somewhere out here you have a public authoritative server for external traffic, and the two contain the same information, but they're different, and the only point is they have different amount of load and different needs for DDoS protection. And Ultra DNS has some complicated system you can sign up for that has many nodes all over the place and a complicated system to distribute traffic among them all for high availability. There are various DNS software packages, and of course you have to keep updating them. Bind was the standard. People used it almost universally for decades, and it had a lot of vulnerabilities. You had to keep updating to the newest version. There's another one intended to be more secure than Bind, but it seems to be gone now. There are many others. There's the Microsoft DNS server, very rarely used because it's very inefficient compared to Bind. And then there's DNSSEC that I mentioned many times. DNSSEC is very much like IP version 6, very complicated, and of very little apparent value for most companies, so everybody's dragging their feet on deploying it. Now, IP version 6 is beginning to be deployed because we really did run out of IP version 4 addresses, and that finally motivated big companies like Comcast to deploy it. But DNSSEC really accomplishes very little and is quite difficult to deploy. So the deployment is just going very slowly. The point of DNSSEC is that when you get data from a server, it will come with a cryptographic signature so you know you're getting accurate data from the right server. And that sounds great. The problem is it only applies to server-to-server traffic, not server-to-client traffic. And the real risk to most people is actually the confidentiality risk of the unencrypted DNS requests on your own network, and it does nothing to help you there. So that's what it does. It signs things with this resource record signature. And so there's a chain of trust. Every time you have cryptographic signatures, you now have to say, well, how do you know if it's the right cryptographic signature? So you have to have this chain of trust, and there has to be an ultimate root of trust somewhere where you trust somebody. Now, in HTTPS, you trust certificate authorities, which are big private companies, like insurance companies. In DNSSEC, you trust the root of DNS. And so here's the root is self-signed, and then org is signed by root, and ITETF.org is signed by .org. So there's your chain, but you have to trust the root, which is self-signed. There's nothing higher to sign it. And in fact, the way this worked, and I think it still works, is they took the root key and they broke it up into like 7 pieces, and they gave those pieces on thumb drives to trusted, famous individuals in the internet community, and they would meet in a room once a year and have a ceremony where they all contribute their part of the key is reassembled, and they verify that the key has not been modified to prove that the root has not been man-in-the-middled or altered. And Dan Kaminsky was one of those guys trusted to be one of the holders of the key. And this is some attempt. The internet community keeps doing this. If you don't trust any government and you don't trust any corporation, you have to invent some kind of community-based root of trust, and that's the one they have for DNS. So it is pretty strange, but ultimately all security relies on trusting somebody. And how can you ever trust anybody? Because if they could like change the internet, they could make an incredible amount of money. So how can you ever be really sure that hasn't happened? And there's just an endless chain of attempts to try to solve this problem, all of them having some flaws. Like one of the things people do is put up records that show they have not received a national security letter. And then they forget to update those, and it looks like they have received a national security letter. It's so anyway, you have a whole series of things. Up at the root, you have a DNS key record signing the root, and then you have various resource records and signatures verifying all the steps that come down from there. All right, so in 2010, the DNS root was signed. That's when it first became available, and ever since then they've had this process I was describing, a group of celebrities being used to verify it every year. So you can see these if you go to a command prompt on a Linux machine like this Mac that has dig. You can observe the signatures of the root. So if I dig rrsig of dot, that is the root of DNS, and I got an answer before, but now I'm not getting one, and that's because I'm now going through a proxy service, which for some reason is blocking this. So I think I'm going to have to go back off the proxy for the moment, so this may interrupt the stream. Let me get rid of that. When I get to the demonstration, there's going to be a complicated mess of networking to try to get beyond the City College firewall. All right, so when I quit using the proxy, let me see what that's doing to the stream. That should cause an interruption. Perhaps not a significant one. Let me watch the people online, and can you see me? We'll see. It looks like the stream is still going. All right, good, thank you. So now let's see if I can do this dig. And I still can't do the dig. All right, it worked earlier, but for some reason it's not working now. What if I redirect this at a different server? Nope, all right. Well, I may abandon this demonstration. Very strange. It worked before class, but now it's not working. Dig DNS key dot. Oh, all right, that one works. I don't know what happened to the other one, but here's some of these cryptographic signatures. There's a lot of them. All right, so there's the DNS key for it. And all right, let's dig ds of org. All right, and there's the answer. Oh, that's right. This is a DS record, which is another cryptographic signature record. All right, and there's a bunch of these. I'm not going to bother with them. I don't really care that much about the details. I've been through it in previous versions of this class, but I think it's not that important. All right, and so there's just these long cryptographic signatures that sign various parts of this. There's the top-level domain org, signed with these long cryptographic signatures, which, as you can see, really clog up your DNS. Anyway, here's the DNSSEC of top-level domains as it moves forward. And I saw a map recently. Almost all top-level domains in America are now signed. But that's top-level domains, .org, .com, .net, .mil. That's really not a very big set. And for you to get any benefit out of it, you would also want the company domains like ccsf.edu and yahoo.com to be signed. I don't think very many of them are signed yet. So as you can see, as of 2017, a few years ago, you see only a tiny amount of the domains were signed. A ridiculously small amount at many hosts. So its deployment is going very slowly because it's hard to understand. Actually, the only thing DNSSEC prevents is the Kaminsky attack, and randomizing the source port, in fact, seems to prevent that. So more and more people argue we shouldn't even bother with DNSSEC. It is slowly rolling out anyway, but it's highly controversial. All right, Cloudflare tried to make it easier. Various people try to make it easier, and it is gradually coming, but a lot of people think it's more bother than it's worth. You can put an extension in your browser to try to validate DNSSEC at the browser level, but none of the browsers are enforcing it by default, which means end users are getting no value out of it yet. Now, there's another way to look at this. If you don't trust the SSL route, because certificate authorities have failed many times, they've been hacked, and some of them have deliberately betrayed people, and there is a persistent issue that you can purchase root certificates from certificate authorities for money, which you're not supposed to do, but everybody needs them. The police need it to do wiretaps, the government needs it to do wiretaps, and your company needs it to intercept man-in-the-middle HTTPS sections, so a lot of people are just buying these fake root certificates and using them, which means you don't really know who you're talking to. So various people do not trust SSL, or TLS, and they would like to use DNSSEC to verify it instead of certificate authorities. If you trust the root of DNS more than you trust the certificate authorities, there is a protocol for that, DANE. I don't think anybody much is using it, but it is an option. All right. And so the DNS protocol is still changing, and like I say, it only secures records to the resolver, not traffic from resolver to client. All right. Then there's another issue too. Suppose you have a server that does not exist, fred.ccsf.edu. Well, you could do a query and get no answer, but that doesn't prove it doesn't exist. There could have been a network issue that prevented you from finding it. So there is a record you can put up to authenticate that that thing does not exist. They invented something called the NEXT record. That was insecure, and they made the NSEC record, but that was bad, and they turned it into the NSEC 3 record, and all three of these are incompatible with each other. This is why DNS turned out to have serious security flaws. It's really very complicated. So there's a transaction signature record to maintain integrity of the records, the messages between two records. And this involves a secret key being transmitted to the other server, which is not good. Public key cryptography would be a lot more reasonable. Then originally it used only MD5, but now it uses more modern hashes that are safer. There's a lot of error messages. But the error messages are unsigned, so you can create a denial of service condition by sending fake error messages. So there just seem to be a lot of flaws in DNSSEC. There's the SIG record, there's the transaction key record, and this used Diffie-Hellman key exchange, but the problem is it's vulnerable to man-in-the-middle attacks. So the problem is all these things were designed decades ago, and cryptography has advanced a lot since then. So what seemed like a good technique 20 years ago has not stayed good. All right, anyway, the software diversification is quite good. There's various servers used, and there's master-slave setup. You have a master that has a master copy of the zone, and then you have zone transfers to make copies and copies of copies. So that's the way it's always set up. And you can configure that in bind to make your thing into a slave server. The other big issue is the 512 responses. Original DNS only lets you have 512 bytes of data per request, which is really not enough for those big signatures. So there are various options. One is to use TCP. So here's CCSF. Had 4 NS records, which is common. You only have a total of 13 records you can fit in 512 bytes. So you can have, everybody has more than one DNS server, unless you're a true amateur. City College has 4, and I think now it has 5. And so you'll have a series of these. So you can use a load balancer, which sends some queries to this server and some to that server. So it all appears to be a single server to the user, but there's a series of servers behind there. That's true of all services, not just DNS. All right, and so you can put a firewall on it, an intrusion detection system, intrusion prevention system. These things all run on hardened systems, typically based on BSD Unix. And older firewalls restricted DNS to only let 512 bytes through. But there's extended DNS, which allows UDP to go up to 4,096 bytes, which is one of the possible ways to extend it to handle those larger records. Now, there are scrubbers. These are used to stop denial of service attacks in progress. So you put on extra servers just to filter out the traffic. So here, normal traffic, you get all these people all over the internet sending traffic, and you just route it all to your customer, and they all come to your server. That's normal networking. But when you turn on scrubbers, you run it through scrubber sites, and the scrubber sites block certain traffic. This was used a lot during the Al-Qassam cyber army attack on American banks after a movie came out insulting Mohammed, and about 10 years ago, and a whole bunch, and a group of religious people sent attacks against American banks, having carefully calculated how many dollars of damage they were doing, and they calculated how many dollars of insult had been created by this movie and wanted to punish it. And they had like 13 waves of attacks, each getting more sophisticated than the last. And there was a network of network engineers communicating the signatures to identify the attack traffic and continually update the filters. There was a secret talk at one of the conferences I went to where they told us the secret pattern of blocking these. All right, so you can monitor to see if your traffic is up by just sending probes, DNS requests sent to them. This is very common to make sure your servers are up. And you got to have backups of your servers, the operating system and the data, because of course they can fail. And you have to back up your cloud servers too, and you have to test your backups. It's fairly common that people deploy backup systems, they don't work, and they don't notice. And when it goes down, they find out they don't really have any backups. If a server goes down, but there are other servers, then you continue to get service, but it can really slow it down with DNS because it'll wait for the first query to time out before it tries another. So it's better to remove the records which point to the failed server. So it will no longer send any queries there. Anyway, let's take a look at Kahoot about this stuff, which is CNET 40, Chapter 5, all right. So, which architecture places authoritative servers in different autonomous systems? All right, that's network distributed. All right. All right, what does Cloudflare use? All right, it uses direct delegation. They have to be your authoritative DNS. So you have to trust them. If Cloudflare goes down, your site is down. All right, how do you provide authenticated denial of existence? Okay, NSEC3. DNS key is just one of those signatures to prove that something is real. NSEC3 is the latest protocol to prove that something does not exist. All right, what system removes the need for certificate authorities? That's DANE. DNSSEC does not prevent certificate authorities at all. DANE is what permits you to make secure connections to web pages, trusting the root of DNS instead of trusting certificate authorities. All right. Well. I got Nick. I think I know who those people are from previous classes. There. All right. Well, let's take a quick look at the last chapter here. I don't plan to do it in much detail. Start another recording. Well,